Hello, my name is Yonatan Calahorra, and I'm an assistant professor at the Department of Material Science and Engineering at Technion in Israel. I'm very happy for this opportunity to present some of our research and results regarding the magnetic and magnetoresistive properties of nickel nanoporous gallium nitride composites. This is a brief outline of my talk. I'll first introduce our interest in multifunctional semiconductors, and then move on to the results regarding the magnetization of nickel-embedded porous gallium nitride and also the magnetoresistance of nickel-covered porous gallium nitride. So when we consider magnetoelectric multifunctionality coupling between electrical and magnetic properties, there are two ways to think about it, an alloy or compound approach and a composite approach. And if we know ferromagnetic materials and also ferroelectric materials, sometimes our composite is both, and that's basically the compound approach. We can also think about taking two different materials and putting them together in a composite form, and in this way induce the coupling between the properties. And the magnetoelectric coupling is, for example, coupled by elastic coupling between two phases. When we consider semiconductors, they also carry inherent multifunctionality. And when these are optically active, it's an optoelectronic coupling. And gallium nitride and related materials are very important in that field. Right now, they're dominating solid-state lighting. It is, of course, what's behind the recent Nobel Prize regarding the blue LEDs. And basically, we have a material that couples between electricity and optics. So when considering magnetic and semiconducting multifunctionality, we can think about dilute magnetic semiconductors. This is the compound approach, and it's responsible for very interesting research topics like spintronics, spin optics, and also electrical control of magnetism. And if we see, or if we take a look about some important examples, for example, in this case, the magnetic state of one part of a PIN junction controls the properties of emitted light, and so that's spin optics. And we can also look at the other way around, so where an applied voltage controls the magnetization of the dilute magnetic semiconducting layer. This approach has some challenges, for example, low Curie temperature, and basically it's some sort of inherent competition between semiconducting and magnetic properties depending on the exact doping level of magnetic atoms. So researchers have suggested working in the composite approach, and this is taking some interest in recent years. And in the past 10 years, some examples about coupling gallium nitride and related materials and magnetic materials. So we can look at this case of a magnetic layer covering an in-gas emission stack. And the magnetization of the layer can control the emission wavelengths. For example, as we see here, it doesn't happen in the uncoated control sample. There's also a spin optics example made using gallium nitride nanorods covered by ferrite nanoparticles. And the composite approach, even in gallium nitride, is working. So our interest is in porous gallium nitride, this kind of material in cross-section. And recently we observed that porosity in gallium nitride can induce interesting piezoelectric properties. That's another type of multifunctionality if you want. Using a PFM, an AFM apparatus where voltage is applied between the tip and the sample, and the AFM records the deformation, piezoelectric deformation, we found that at about 40% porosity, the measured or the effective DP3 piezoelectric coefficient was 2 or 3 times higher than that of bulk. So that's very inspiring in terms of piezoelectricity in itself, but also we thought it might be interesting to make a composite material to fill these pores with something, and that something can be a magnetic material. So we have this process of electrochemically etching the gallium nitride to make it porous. And then we consider 2 routes to create the composites. One is to further electrodeposit nickel inside the pores, or hopefully inside the pores, and also to sputter nickel directly on top that layer. Let's see some of the results. First, we can look at the effect of pore size. And our process was calibrated such that we knew how to control the pore size by, for example, increasing the etching bias during etching. And then the question is, how will that affect electrodeposition, and how will that then affect magnetization? So we see 2 samples with different pores. We have larger pores with higher etching biases and smaller pores. And we can see that actually the electrodeposition on top of the smaller pores resulted in a layer, while in the larger pores it resulted with less of a layer and more of embedded nickel. And this is not a direct result of the pore size, but also some coupling between the pore size and the conductivity of the sample, and the smaller pores were more conductive, and hence the electrodeposition took place on top. So what about the magnetization? We carried out a series of VSM measurements, and we can see that in the small pores, when we look at the in-plane and out-of-plane corrosivity, there's a large difference here in squares between what we get when we have an easy axis, which is in-plane with lower corrosivity, and hard axis, which is out of plane. And this distinction between in-plane and out-of-plane is dramatically reduced for the larger pores with nickel embedded inside. It makes some sense, right? It's no longer a thin film. So what about the effect of the position duration in the larger pores now in samples where nickel is more embedded? So if we look at control samples deposited on ITO electrodes, we see a classic sort of easy axis, hard axis behavior. This also happens in the thicker layer deposited on gallium nitride. And when we move on to the shortest most deposition times we use for the larger pore samples, we actually see a very interesting response. So the in-plane, out-of-plane asymmetry is almost lost. And we also see some peculiarities in the corrosivity, high corrosivity, asymmetry in corrosivity, and all these behaviors sort of die out and transfer to a more thin film-like behavior when the electrodeposition is at longer durations, moving on to fully thin film for thicker films. So let's focus on these 2 shortest or shorter deposition times. And we actually see in EDS that we have nickel embedded inside the porous layer, but not as these columns that we thought we would get, but more in these clusters of or nanoparticles of nickel. We also see more oxide in this area. And what we actually think is happening here is that we get these nanoclusters. These nanoclusters get slightly oxidized, and then the interaction between the nickel oxide and nickel could present as an exchange-wise interaction and cause some of these peculiarities in the corrosivity. And as we saw earlier, as more nickel is deposited, the overall weight of the nickel oxide is reduced, or the relative weight, and then we see less of these effects and more of the thin film-like properties. What about nickel sputtered porous gallium nitride? So this is still work in progress, but if we look at the thinnest both layers deposited less than 100 nanometers, we see again interesting features here in corrosivity, but we also see lack of the in-plane, out-of-plane asymmetry. And basically we think that some nickel penetrates the top of the porous layers, and if the total film thickness is relatively low, then the contribution of this infiltrated layer is stronger. Next, if we look at the magnetoresistance of such samples, although this time with thicker nickel layer, about 200 nanometers, we carried out a series of magnetoresistance measurements, starting at 300K, going back to 200, and then moving back to 300. So the first thing we notice is that at room temperature, the magnetoresistance is positive, and that's uncharacteristic of nickel. We also notice that there is in-plane, out-of-plane asymmetry, and that's uncharacteristic of pure gallium nitride. So we realized that the conduction here is actually quite interesting, and something is going on here. We see low field increase, and then this significant difference between the in-plane and out-of-plane magnetoresistance. Moving on to 200K from 300, the magnetoresistance changes dramatically. So the overall resistance increases, meaning that most of the current is carried not by the nickel, but actually by the gallium nitride layers. But now its characteristic is different. It's negative, although maintaining a difference between in-plane and out-of-plane. And then going back to 300K, we see that the low field features that we observe here are gone, but we remain with the in-plane, out-of-plane asymmetry, and also the difference or the sweep direction related control of the magnetoresistance curve. So what we want to do is take a closer look at it, and by a parabolic fit to the descending branch in the positive fields and the ascending branch in the negative fields, we find the local or the expected local minimum of each magnetoresistance curve, and we found that these are very different. And that is our indication that the transport in this structure is actually controlled by the magnetization of the layer, even though the transport is not in the layer itself. It's just a semiconducting gallium nitride transport. So it is shifted with sweep direction. That's the magnetization. Our thought is that it is coupled. So the strain of the layer, of the magnetic layer, is coupled through the piezo resistance of the gallium nitride. So to conclude, we examined two types of composites of nickel and porous gallium nitride. We've seen how gallium nitride porosity affects the magnetization and the deposition of the layer. And we also seen some evidence of the magnetization effect on gallium nitride transport. So that's some interesting magnetic semiconducting coupling. I'd like to say thank you to Carnarian and Oliver group members in Cambridge where this work started, mostly Joss Dawson, who was a master's student in the group, did a lot of this work. And right now the work is continuing in my group at the Technion, with Yana heading that. And of course, our funding. And I'd like to thank you for your attention, and please feel free to write me, contact me, and I'll be happy to take any questions. Thank you very much.